Good afternoon, everybody. I'll start by trying to use this mic. If you can't hear me at the back, I will use the other mic. So, my name is John Heasman, and I work for NGS. Earlier in Mike Kemp's talk, somebody asked a question, who or what is NGS? NGS is a security consultancy headquartered in London. We're soon to open a West Coast USA office in Seattle. And we specialize in product assessment and vulnerability research. So, I'm here to talk about BIOS rootkits, firmware rootkits. And this is pretty much what I want to cover. In 2006, I did some research and first produced a proof of concept BIOS rootkit that abused the Advanced Configuration and Power Interface, ACP. So, I'm going to start by giving you a brief overview of that technology and its limitations, which led me on to looking at the PCI bus. Then I'm going to talk about actually what the PCI bus is, how PCI devices actually work, and the meat of the talk is going to be abusing a component of PCI devices known as expansion ROMs. That dovetails nicely into abusing PXE, Intel's pre-boot environment. We're then going to talk about actually trying to detect these things, trying to prevent them in the first instance, and that leads into a discussion on trusted computing. And I'm going to discuss Vista installed on a box with a TPM, and I'm going to talk about whether BitLocker actually prevents this type of attack. And then I'll leave you with some questions at the end, questions for further discussion. So let's get started with ACP. As I said, I presented this research in early 2006, and essentially I was looking at ways of putting a rootkit in the BIOS. And the first thing that struck me is the BIOS is obviously pretty low level. It's code that will execute when your machine turns on during the power on self-test. So how do we actually go from storing code or data in the BIOS to actually deploying our Windows rootkit, for example, our rootkit that will hide processes, hide files, make covert network communications? How do we go from the BIOS, which is extremely low level, to deploying something that's actually quite high level in regard to the operating system, how it interacts with the kernel? And ACP was an easy way around this. Essentially, as I said, ACP is the Advanced Configuration and Power Interface, and it basically handles power management. So it actually replaces the old APM, the Advanced Power Management spec. The way it will actually work, or the way APM used to work, is supposing on your notebook you wanted to retrieve some sort of power setting. For example, you wanted to know how much charge is left in your battery. The operating system would simply call into an APM interface that was implemented in the BIOS. And so these were implemented by the vendor and were often very buggy. And your machine would hang for no reason, and you'd say, you know, stupid Microsoft, when in fact it was the vendor's buggy APM code. So they moved towards ACP. Consortium was formed with all the usual kind of players, Intel, Microsoft, HP. And the idea with ACP is that they've abstracted this, so that supposing you want to find out how much charge is on your battery, the way ACP would work is the BIOS holds some tables, data tables, which contain virtual instructions, the ACP machine language instructions, which explain how to actually retrieve the amount of charge, for example. The operating system will load a device driver, one of the first it will load, in fact, that actually has a virtual machine inside it that is capable of interpreting these machine language instructions that are stored in the BIOS. And basically, this machine language instruction set allows us to interact with the system. So, for example, if on a particular motherboard we need to do some certain I/O to retrieve, say, the temperature the motherboard is running at, using ACP we can abstract that so that basically the vendor ships the device driver for ACP, the operating system vendor ships the device driver for ACP, and then the motherboard vendor ships the BIOS with the ACP tables which say you need to implement these specific instructions in order to, say, read the temperature off the motherboard. So this machine language instruction set is actually very powerful. One of the things it allows us to do is interact with system memory. So the basic attack for the ACPI BIOS rootkit was, we take a BIOS for your motherboard, we download it, say, off the vendor's website. We crack it open. BIOS that you'll download and actually flash to your motherboard is typically just an archive of some form. So we split it into its components. And you'll see one of these component files is essentially these tables of AML. And we actually modify these AML tables so that in addition to carrying out these virtual instructions that are required to, say, read the temperature off the motherboard, it will also execute our malicious AML. And as I just said, the AML instruction set actually lets us interact with I/O space and memory space. So the idea is that when the machine boots up and the ACPI device driver loads and it starts consulting these AML tables, it will actually execute our virtual instructions, and our virtual instructions will basically just patch our rootkit straight into memory, overwriting whatever kernel code page or data page we need to. So this is conceptually what ACPI would look like. You have your hardware at the bottom, and then you've got your BIOS that's typically stored in firmware that you can reflash. Conceptually above that we have the ACPI tables and a little scratch area for storage, the ACPI registers. On top of that we have the ACPI device driver, and that is a kernel module. And the kernel also has some OS power management code that will basically allow applications to call into the kernel and say, for example, how much charge is left in the battery. Some limitations of this technology. Firstly, we have to be able to reflash the motherboard BIOS. And there are technologies to prevent this. For example, Intel and Phoenix have the ability to only flash their motherboards with signed updates. So we simply cannot get modified AML tables on there. The second limitation is the operating system has to load an ACPI device driver. Typically, you can still boot your operating system if you don't load the ACPI device driver. It may not recognize all your devices because, in addition to power management, ACPI also handles configuration. It's actually a replacement for plug and play. But you can still get your operating system booted somehow without ACPI. And the problem is, if you can load the operating system without ACPI and you suspect you have an ACPI rootkit, then you can do the standard cross-view detection. So essentially, you scan your system with ACPI enabled, you scan it without ACPI enabled, and then you compare the two, and if there are any discrepancies, that may indicate there's a rootkit. And thirdly, I said that through this AML, we can actually interact with system memory and the system I/O space. One of the things I noted in my proof of concept was when I actually wrote to certain kernel code pages on Windows, it generated an event log error saying, you shouldn't be doing this, but I'm going to let you do it for compatibility reasons. So it wouldn't take much for Microsoft to actually, or indeed any ACPI device driver, whether it be the Linux one, the Solaris one, or the Windows one, to actually sandbox the AML interpreter to say, you shouldn't be overwriting kernel code pages. I'm not saying that would totally prevent attacks. There'll probably be various data structures we can still target, but it would certainly make it easier. It would certainly thwart my initial proof of concepts. So those limitations, I was still looking for a rootkit that could persist on the system even if you reinstall the system. I mean, that's my overall goal. And so I'd already considered the BIOS, but the main limitation is systems that have a signed BIOS, we can't get our code on there. So I started looking at other devices that have firmware on a modern PC. And there are literally tens of devices. Pretty much every component in your PC has some firmware which can typically be updated from the system itself, as in we don't need to remove the component, nor do we need to remove the chip off the PROM off the card itself. So the PCI bus looked very appealing. On a typical machine, you'll have several PCI devices. And one thing I'll make clear in my terminology is that when I talk about PCI, I'm actually talking about PCI, AGP, and PCI Express. So pretty much all of those technologies fall under what I'm going to call PCI. So some questions to consider, firstly. So if you consider every machine on your network, could you tell me exactly which PCI devices are in every machine? And if you could do that, could you tell me where you sourced them from? Could you tell me how many people came into contact with that card since it left the factory and ended up in your machine. If you could tell me that, could you tell me which of the cards can you actually update the firmware on? If you could tell me that, can you tell me what firmware is currently on your device? And if you could tell me that, then could you answer whether you can actually trust the integrity of that firmware? And I'm guessing in 99% of the people here, like pretty much in general across the board, no one's going to be able to answer all of these questions. Maybe certain governments can, but certainly most corporations that I've seen, they have a hard enough time knowing what machines are on their network, let alone what cards are in those machines, let alone whether they're flashable. So I'll give a very brief introduction to the PCI bus. Obviously it's a computer bus for attaching peripherals to the motherboard, developed around 1990 by Intel. And essentially, the way it works from an operating system perspective is the operating system will enumerate the PCI bus and will basically ask each device, what are you, what type of device are you, give me some sort of identification that lets me load a suitable driver. And that information is stored in the PCI configuration space on the card. And basically, as I said, it holds some various codes. It holds a class code, a device code, so that it can say, I'm a graphics card, I'm a VGA card, whatever. It also contains a human-readable identification string. So, for example, in Windows, when you hot plug some sort of device in, say USB, a similar thing, it's able to pop up a box saying it's recognized the hardware. It may not have a driver for it, but it's going to print to you the string saying it's a camera or whatever. Conceptually, we have the concept of a bridge. You may have more than one PCI bus, probably have a PCI Express bus these days. And we have the concept of devices, though a device can have multiple functions, and a function really is what we would consider an actual device, as in something that can actually do something. But it could all be integrated into one logical device. So you can see here's a dump of the PCI bus on my notebook. And have a few multifunction devices. So the interesting thing about PCI devices is that some of them require some initialization. And the way this initialization happens is essentially there is a ROM on many PCI cards. And this ROM holds this initialization code, typically x86 code. So simply straight x86 code that will be executed by the main CPU on your system. And what actually happens during the power on self-test, when you first turn your machine on, is that your BIOS will scan the PCI bus and it will look for all the cards that have expansion ROMs. And when it finds an expansion ROM, a card with an expansion ROM, it will ask it to copy its expansion ROM from the card itself into physical memory. Once the BIOS has done this for all of the cards in your system, it will simply sequentially execute those ROMs. So we've gone from some code that was stored on the PCI card itself. It's now in physical memory, and it's now being executed during the power on self-test. So this is essentially before anything has been printed to your screen when you've turned it on. Certainly before the OS loader has started, and obviously before the operating system has started. So when you think about this from an attacker's perspective, this is quite handy. We're actually executing code in the BIOS that was stored on a PCI card. In practice, as I said, this is used for initialization. For example, your PCIe graphics card is likely to have an EEPROM. The difference between an EEPROM and an EEPROM is whether you need to actually take the chip off the card to flash it. EEPROMs can actually be flashed while they're on the cards by supplying a current rather than the old-fashioned PROM method of an ultraviolet light and then burning new image onto it. So your graphics card, your PCIe graphics card, will have an EEPROM that will contain some initialization code that during the power on self-test is copied to RAM and executed, and that will actually hook interrupt 10 in the real mode interrupt vector table. The interrupt vector table essentially gives you access to the set of services exposed by the BIOS and various cards that your bootloader has to rely on. So, for example, by hooking in 10, it allows us to actually output characters to the screen. So when your OS loader says, starting grub or NT loader loading Windows, basically the PCI graphics card has hooked int10 and its code is being executed there. Expansion ROM, this is kind of what it looks like. You have a signature, a couple of bytes, and then you have at offset 3, essentially just an entry point into the ROM itself. And so the signature bytes are used so that the BIOS, once it's copied the ROMs to RAM, can scan through RAM quickly and say, here's an expansion ROM, I'll just jump to offset 3. They also have a checksum as well. So the problem is really, how do we go from this code that's executed in real mode, 16-bit real mode, how do we go from that code in the BIOS, or executed during the post, sorry, to actually deploying our Windows rootkit, or our Linux rootkit? There are various ways we can do this. Essentially, the OS loader has to rely on the IVT, this vector table, interrupt vector table, because the OS loader doesn't know what hardware you have. It doesn't know how to access the disk. It doesn't know how to access the screen. So it has to rely on some services exposed by the BIOS through the IVT. So EI produced a boot sector rootkit a couple of years ago, and they actually hooked int13, I think they should be int15 for disk. And what they were able to do is, every time OS loader called int15 to read something off disk, they would actually scan the byte stream and modify it in place. So they would look for a particular device driver being loaded, in this case the Ethernet driver, and when they spotted it being loaded, they would actually patch it on the fly so that they could put their backdoor into it. So this was a nice technique. I guess one of the downfalls of this technique is you're looking for a specific string of bytes. If you upgraded your Ethernet driver, for example, you might not spot that. It's also a little bit clunky. So I looked for another technique, and I started looking at int10, which is the video interrupt. And what I noticed was int10 is called by the system BIOS. Well, this is unsurprising, because if you want to output characters to the screen, you have to call int10. And when you turn your PC on, it says Dell or whatever. That's calling int10. NT loader, the Windows OS loader, also called it. That was also unsurprising, because it says NT loader and it displays that bar at the start. Slightly more surprising was that the protected mode 32-bit kernel, NTOS kernel, the Windows kernel, also called int10. And so this was a little bit confusing at first. I will explain it. I'll take a little detour to get there first. Recap of x86 operation modes. So what modes can the processor run in? It can run in real mode, which is essentially how Windows 3.1 and DOS, etc. ran. And essentially, you have no concept of memory protection or multitasking. So it's pretty much not secure. Protected mode, we now have the concept of privilege levels. We have four rings of privilege, though most operating systems only use 2, ring 0 and ring 3. And we also have the concept of memory paging. And essentially, all operating systems these days are built in protected mode. And it's the job of the OS loader to actually transition the CPU into protected mode to then load your kernel. There's another mode which is quite interesting. V8086 mode, also called virtual real mode or VM86 mode. And this essentially is a hack for compatibility. This lets you run those real mode applications, DOS games for example, under Windows, under your protected mode environment. And it does this with a few tricks. As far as the old school real mode application running under Windows thinks, it really thinks it's running in real mode. So it will call interrupts, for example, int10, and it will access memory thinking it's accessing the physical memory. In reality, it's still accessing virtual memory, and it's still accessing memory within its own process, but it doesn't know this. So the key points here is that memory paging and memory protection is still applicable, and VM86 mode really is a hack. So what I noticed, and what I deduced, is that when the Windows kernel calls int10, it must have switched into V8086 mode for some compatibility reason, some hack. And sure enough, I found an export in the kernel, function in the kernel called K386 call BIOS. And we can see that it's actually called from the VGA driver, vga.sys. And basically, KE386 call BIOS switches the processor into V8086 mode and does an int10. And the reason I think it's doing this, I didn't look into it in great depth, but the reason it seems to be doing this, it seems to be asking your video card, what legacy video modes do you support? What legacy screen res do you support? And it does this fairly late in the boot. The way it actually switches to V8086 mode is fairly interesting. It maps the assembler code it requires, in this case the int10 you see there, into the CSRSS process in Windows, and switches to V8086 mode and starts executing it. The problem is, after you've executed your int10, how do we get back into protected mode, and how do we carry on execution from the kernel from this KE386 call BIOS function? How do we actually get back there after switching into V8086 mode? And it uses something which is kind of strange. It's called a BOP, and it's a bad operation, basically an invalid opcode. So the CPU starts to execute this C4-C4-FE sequence, and it basically says, this is junk, this is not an actual operation. And this is deliberate, because the BOP will actually then cause an invalid opcode fault, which will cause it to jump back to kernel. The kernel then detects, we've come in via the BOP, this is a special case, so I'm going to carry on from over here. So it's kind of funny to look at first. But we can hack this in a cool way. Basically, as I said, the BOP generates an invalid opcode fault, which the kernel detects. The kernel detects that it came from a BOP, and the kernel then uses a specific structure, the VDM TIB, thread information block, to actually resume execution. And the interesting thing is that structure is in the low 1 megabyte of CSRSS's process space. What this means is, when we execute the int10, we're executing our code, because we've already flashed the graphics card, we've hooked int10, Windows is booted, it's called int10, so it's now executing our code in V8086 mode. The name of the game here is to modify this VDM TIB structure so that when the kernel actually returns, it's now going to use our values to return. After we've modified the VDM TIB structure, we just allow the int10 function to carry on as normal, retrieve the legacy screen modes, whatever it's trying to do. Slight complication is that we can't modify the register values in this VDM TIB context structure directly, because the fault handler looks at certain registers to see it as a special case, to know that it came through this int10 special case. One register we can modify is there's a stack frame pointer, and we can modify this to make it point to our own fake stack frame, and ultimately the kernel will use this stack frame to work out where to return to, the parent function, and when it does so, it returns to our code. And so the long and short of it is, having gone from reflashing somebody's graphics card and putting the int10 hook in ourselves, we have the ability to execute standard code, 32-bit protected mode code in the Windows kernel as it's booting up. I guess I've explained this very quickly. It takes some going through. It certainly took some tinkering to get it working. The takeaway point here is that EI used int 15, I used int 10. You can probably use a whole host of other interrupts. The point is that the OS loader is dependent on the services exposed by the BIOS via the interrupt vector table. So any services it calls, we can probably hook and do something funky to end up getting code execution. It's basically just a dependency. The OS loader cannot do anything on its own. It needs to use this IVT. Once I got code execution, and I demonstrated a simple, the hello world of Rootkits, which on Windows is the 1-byte patch to disable all access control. After that, I made it a bit neater. I started removing hard-coded addresses. You can think of this like an exploit, where your first pass of it has some hard-coded addresses in, which means it only works on a particular service pack, a particular version of Linux. And then your later revisions, you want to try and remove all dependencies on the system so that it can just run, automatically work out where the exports are it needs, that kind of thing. I also played around with adding some compression at the start, so I have like a little decompressor function, which then allows me to compress the bulk of the rootkit. Because you may ask, well, how much space do you have on these cards? The answer is, obviously the vendor's got their code on the card, so you need to kind of either get rid of the vendor's code, which is probably not an option because it's probably there for a reason. If you just wiped your VGA BIOS off your graphics card, your machine may still actually boot, and when it gets to, say, Windows or Linux, it would be fine, but you just wouldn't see anything until then. So removing their code, it probably isn't a good reason. Even if the machine would boot, it's not very stealthy, obviously. You could potentially shrink their code. You could maybe compress their code and put your compressor at the start to free up some more space. The reality is you're going to have between about 1 and 5 kilobytes on every ROM I've looked at. So compression may well be required. To give you an idea of rootkit size, you can write a simple Windows processing hiding rootkit that takes about 1.5K. I also wanted to provide some means of updating it. So I came up with the idea of, we can just reflash the card with the new code. How do we actually go ahead and get the new code? How do we get the update? My first pass on Windows was we used TDI, which is the networking layer in the kernel, to go off and make a HTTP request or whatever. But that's not very reliable because if you have a personal firewall, anything that's also kernel level that's restricting network traffic out could get caught. So I came up with a new objective, which was let's try and update our rootkit pre-boot. And this brings me on to PXE. PXE is Intel's pre-boot environment, which probably most of your notebooks have, and most desktop machines also have. Essentially, it allows you to, from the CMOS setup screen, select network as the device that you want to boot off, and boot off the network to essentially load your machine as a diskless workstation, or to ghost the machine, or to actually re-image the machine, like rebuild the machine entirely. And so essentially, all PXE is an expansion ROM on your network card. And this expansion ROM implements some core protocols, DHCP so we can get a MAC address, and then TFTP so that we can ask a PXE server to actually send us an image to execute. And PXE used to be implemented as one big ROM that just did everything. But the way vendors seem to go these days is they've kind of made it a bit nicer. They've split it into a series of ROMs. I'll explain how they've done it in a second. The idea being that, as I said, these ROMs are simply x86 code. It doesn't matter whether the PXE ROMs are really on the network card or they're in your system BIOS. It really doesn't matter. So by splitting it into these modular ROMs, we can actually move the code around, put it on other cards, put it in the system BIOS. It's actually quite easy to modularize PXE. Here are the main components. We have UNDI, which is the lowest level API, and UNDI is the kind of card-specific API that says, how do I actually send a frame onto the network, and how do I actually receive one? Next, we have a pre-boot API, which is responsible for housekeeping. It initializes the UNDI ROM, and it also starts executing the base code. And the base code is essentially the PXE application that will say, welcome to Intel's boot manager, looking for DHCP server, whatever. We have a TFTP and UDP API, kind of self-explanatory, just simple API for sending and receiving. And then we have the base code, which, as I said, is the actual application that's going to make use of those three APIs. So we can abuse PXE, because PXE, as I said, is just a ROM on a network card. Chances are we can reflash that ROM, so we can rewrite the image. So we can take Intel's image on your network card, we can pull it off the card, we can patch it, we can put it back on the card. And we can hook the base code so that instead of going off and executing the standard Intel boot application that says, now loading image off server, stealthily goes to your rootkit controller and asks it, do you have an update, can I download it? The way we're actually going to do this is, firstly, we need to hook int19. Int19 is essentially when the system comes out of post, the power and self-test, and it's actually going to start loading something, it calls int19. Int19 essentially consults the IPL, which is a list of the boot devices in the order you selected in the CMOS, so that it knows which device to go off and boot. By hooking int19, it simply means that regardless of whether you said you want your C drive to boot first, your network drive, your CD-ROM, if we hook int19, we always win. We always get our code executing before anyone else. So we get our code executing, and what we do is we call the IPL to initialize the network layer, and we call our base code. And our hacked up base code detects that, in this case, it's our rootkit coming from int19 that's calling it, and we actually end up executing our alternate payload. And that alternate payload now has access to a TFTP, UDP, DHCP API. And so all this is happening, obviously, before your OS loader has got control. And essentially, at this point, we can do DHCP, TFTP, UDP. So we can fire off a UDP packet, say disguised as a DNS packet to our rootkit controller, saying, do you have an update? If it says yes, we can TFTP the update into memory. We can either then flash it onto the card, or we can just execute it straight from there. As I said, the kind of way you would do that in the field is you would take the existing Pixie ROM, patch it, put it back on. I didn't have time to do that, nor did I particularly want to start disassembling Intel's code. So I looked at Etherboot. Etherboot is an open source Pixie ROM creation tool, and it supports pretty much every network card going. And it also supports tons of protocols above and beyond the Pixie spec. So they even have a simple TCP stack, and they even build HTTP on top of that. And essentially, once you've compiled Etherboot and configured it, it will dump you a ROM that you can then just burn straight onto your network card. So because it's open source, it was nice and easy to hack up. If you use this, it would be easy to detect that it was Etherboot, and I'll talk about detection a bit later, though we could make it harder. As soon as I downloaded Etherboot, the first thing I did is comment out all of the verbose options and comment out anything that did any output to the screen. So basically, when my Etherboot ROM kicks in at boot, you see nothing, and it's just sent that packet and already done everything by the time your OS loader kicks in. So this is essentially how you modify Etherboot. As I said, we have to hook the IPL table int19 so that we definitely have control at boot. We send out a UDP heartbeat disguised as DNS. We check the response. If the controller indicates there's an update, we download it by TFTP, and then we continue boot as normal. Some improvements that could be made. Obviously, we could encrypt it, and we could maybe sign our code so we know it hasn't been tampered with. It's kind of nicety, but not required. Compression or delta updates would be a good one. And this final one, scheduled updates, is actually a more of a realistic one. You may not want to send out this heartbeat packet every time the machine boots. So from our code, we can check the real-time clock, and maybe we want to update every month, or every week, or after every patch Tuesday, or suitable time. An interesting point I touched on earlier is expansion ROMs. All they are is x86 code that is copied from the card to RAM and executed. So really, it doesn't matter what the code does on each card. As in, just because it's a network card doesn't mean we need to store the Pixie code on the network card. We could store the Pixie code on your graphics card if you've got space. We could put it in the system BIOS if we're able to flash it. We could even just make a distributed rootkit that would basically, we could split it across multiple cards. So I'll now talk about detection and prevention. So the first thing to remember is that, as I keep saying, these ROMs are copied to RAM. And they have a signature and a checksum. So why don't we just scan physical memory looking for this signature and basically dump every ROM we find and then do some analysis on them. On Windows we can access device physical memory. Microsoft have actually closed off access to that on Win2K3 SP1. On Linux we could use KMem. You probably want to be doing this from kernel anyway, because if you suspect you have a rootkit, you don't want to be operating in user mode. To give yourself any chance of detecting it, you have to be operating in kernel. Once we've actually captured all the ROMs out of memory, how do we know if we have a rootkit? There's some basic questions to ask. So firstly, what interrupts does the ROM hook? If we identify the ROM as the one that came from our graphics card and it hooks int10, the video interrupt, that's fine, that's probably not suspicious. If, however, our network card is hooking the video interrupt, that's kind of suspicious. Does it contain 32-bit code? These expansion ROMs are executed while the processor is still in 16-bit real mode. So if you actually disassemble it with something like IDA Pro, and IDA says, look, I found this chunk, it looks like 32-bit protected mode code, that's probably suspicious. In the case of Etherboot, it may not be suspicious because Etherboot actually swaps in and out of real and protected mode. But depending on what the ROM is, it's probably something that you should flag as alarm bell. Does it reference any particular addresses? Do we have things like the base address of the kernel? Anything that might look suspicious? And lastly, kind of the catch-all, what does the ROM actually do? So if you're willing to step through the disassembly and actually work out what the hell the thing's doing, that's probably a good way of detecting it. Slight problem. Often the ROM we dump from memory isn't quite the ROM that's on the card in the first place. And this is deliberate. And basically, the rationale behind this is that the ROM contains some initialization code, which you're only going to ever execute when the system boots. When the system is powered on. So really, once that code has been executed, we can throw it away. And what you'll find is that a lot of vendors actually do this. So they'll execute the init code, which will, at the very last thing it will do, is fix up the image by rewriting the signature much later down and recomputing the checksum. And basically indicating to the BIOS that any memory preceding that signature is now valid to be overwritten with something else, another ROM, for example. So to be thorough, just simply scanning physical memory, it won't capture the full contents of the ROMs. There's a way around this, and basically if the BIOS is able to execute instructions to dump the ROM off the card, then so are we. And this is a well-documented chapter in the PCI spec. You basically do I/O to the configuration space, and you can tell it to dump the ROM into a particular location in physical memory, the full ROM. Difficulties in detection. Well, the first one is kind of a rootkit detection point in general. The nature of rootkits are that signature checking is insufficient because a rootkit has probably been written for a very specific purpose, and the chances are your AV software has never seen it before. Then we have the whole IDS, the whole polymorphism, Packer's self-modifying code, as Datagram talked about. Essentially, we can make this thing hard to detect, and if we're planning on rootkitting an entire corporation, we can make every rootkit look different, even though they're the same. And basically, exactly as we saw in the last talk, those tricks of different instructions, reordering instructions, inserting NOP equivalents, it's exactly the same because we are, at the end of the day, just dealing with x86 code. So this kind of makes it difficult, and it pretty much moves the problem of detecting this kind of rootkit into the realm of malware analysis. So we can do some dynamic analysis using emulation or virtualization, VMware, or emulators such as Box. So you can actually capture the ROM off the card, as I talked about in the last slide, and then try and load it into Box. And Box is an open source x86 emulator with an integrated debugger that gives us absolutely full control of the emulated machine. So we can step through the BIOS, we can breakpoint at any point, we have absolutely full control. The problem with this is if you've got, so for example, if you copy the ROM off your graphics card and try and stick it in Box, it's not going to work because the ROM will start talking, when you execute the code, it will actually start talking I/O to the graphics card, and obviously your emulator doesn't have that graphics card, can't properly emulate the hardware. So you can typically only do limited dynamic analysis. If you can identify what you suspect as the suspicious rootkit code that is unpacking some other code or using self-modifying code, then you can probably get quite a way using Box. But really, static analysis, as in hardcore disassembly, may be the only real way to actually work out what's going on. Talk about prevention for a bit, and this is pretty tricky. Pretty much no PCI or PCIe or AGP cards these days have a write protect jumper for updating the firmware. As you're probably all aware, most motherboards have this option, have a physical switch, a physical jumper that you can basically write protect so that the BIOS cannot be updated. As it happens, most vendors still ship with that jumper set so that you can write to the BIOS. Similar rationale behind PCI cards. When they produce the card, they don't think that someone's going to try and rootkit the card. They just think of their consumer that wants to download the latest version because whatever game they're trying to play doesn't work on the graphics card, so they want to be able to flash it and they don't want to have to take it out of the machine. The PCI cards, typically the updates don't require, don't need to be signed in any way. And again, it's like, well, why would you want to put your own firmware on the card? You're only going to probably screw up the card in the first place. And from a cost perspective, if you now have to add some maybe extra chip on the card to actually do some verification of the signature, and then you've got the whole key management, and it becomes a headache. So most vendors just simply aren't going to go there. Up until now, I haven't really talked about how we actually reflash a card. Typically, we do I/O. So we do the assembler instructions in and out to the PCI configuration space. If you download a vendor utility to flash the card, so you go to ATI and you download ATI Flash and you disassemble it, you'll probably see it's doing something like this. It's using how get bus data, obsoleted kernel function. More likely it's using ERPs on Windows to actually do I/O. So theoretically, in terms of prevention, you could hook these, your protection software could hook these and basically say, try and capture whenever you're trying to update the card and say, do you really want to do this, or prevent you doing it. The real problem is, as I said, to reflash the card, you just need to do in and out. So all the other two functions that I had on the last slide, all they are simply wrappers around in and out. If the attacker can just issue those instructions directly, then they can reflash your card. And trapping I/O is a difficult problem. From user mode, from Ring 3, on both Linux and Windows, you only have limited access to the I/O space, because why should you have full access to all these devices as a low-privileged user? In Ring 0, in kernel, you have full access to the I/O space, as you would imagine. There's a couple of interesting quirks. On both Linux and Windows, we can change the I/O privilege level to allow us to do unrestricted I/O from user mode. On Linux, I believe it's the IOPL syscall, which you have to be admin to use. On Windows, it's NT set information process, undocumented export from NTDLL. Essentially does the same thing, and you have to be local system. So you have to have the SETCB privilege on Windows, so you have to be local system. So I guess the protections prevention software could hook NT set information process, but really, if the attacker's on your machine and they can get into kernel, more things to worry about. Yeah, I mean, these are really some ideas, but if the attacker is really wanting to put a rootkit on your PCI card, they're probably skilled enough not to trigger any of these. So what about trusted computing? Does that solve our problems? So many notebooks and many high-end mainboards these days have a TPM, Trusted Platform Module. And essentially this piece of hardware is the cornerstone of trusted computing. And it's a microcontroller that has a few basic functions. So it can do your standard crypto, and it can create and protect and manage keys. It has the controversial unique endorsement key, the unique identifier for your machine, which there's all the DRM concerns about. But what we're really interested in with regard to this kind of attack is the platform measurement hashes. And essentially, the way it works is that when you configure your system with the TPM, various measurements are taken for the first time. I'm actually going to skip to a different slide deck for a second. These are a couple of slides from Douglas MacGyver's presentation, Hack in the Box, last year. Douglas MacGyver works for the BitLocker team at Microsoft, and he gave a really good presentation, a really kind of candid, like warts and all presentation on exactly what BitLocker does. So I highly recommend that. And basically, these boxes here are the components that are measured. We measure the BIOS, the master boot record, boot sector, and the OS loader. So the very first time you run, say, BitLocker, and you initialize your TPM, you'll take these measurements. So you'll basically take a hash of the BIOS, hash of the MBR, hash of the boot sector. The idea being that on subsequent boots, you can then remeasure these quantities, rehash the BIOS, and if it's changed, then essentially you can flag that as potentially troublesome. And these measurements are stored securely, protected by the TPM. Now, the main problem with, say, BitLocker, because essentially what this doesn't show is that another event that is considered are the PCI expansion ROMs. So we have this chain where essentially the BIOS is first verified. If the BIOS is good, then it will start dumping the PCI expansion ROMs from the card into RAM. The expansion ROMs are then also checked. So if we've modified, if for example we had physical access to your machine, we took your graphics card out, we reflashed it with our rootkit, stuck it back in, this is the point that the TPM would say, okay, this measurement has changed, there could well be a rootkit here, or something's gone wrong. So based on what I've said, it sounds like TPM and trustworthy computing solves this problem. However, skip to the right slide. As I said, this is a highly recommended presentation for anyone that's interested. The slide on boot rootkits. Let's go through these. So BitLocker detects boot rootkits installed offline. So your machine's off, somebody has physical access, they change something, as in they change, for example, the ROM, expansion ROM on your graphics card. BitLocker detects this. BitLocker also detects online boot rootkits. What do we call about that? What do we mean by this? Essentially, we mean that your operating system is running, someone compromises your machine, and they try and stick a boot rootkit on there. So, for example, they change the master boot record, or they reflash your graphics card. This is the case that they're BitLocker unaware. And the word unaware is kind of pivotal here. So BitLocker will detect them. It will detect that something has changed. However, BitLocker does not protect against boot rootkits that are BitLocker aware. So if I compromise your machine and I know you have BitLocker running, essentially what Douglas MacGyver is saying here is that I can reflash your graphics card and I can reseal the TPM measurements. And basically, as far as your system is concerned, it doesn't know anything has changed, or it thinks the user has endorsed a change. So basically, as it stands, BitLocker prevents offline attacks, but does not prevent online attacks.
How come the attacker can do that? Aren't the measurements protected by the special controller on the motherboard?
Well, essentially, the way it was explained to me by Douglas MacGyver was, if you're running code in kernel, you can turn off BitLocker anyway. You have to be able to do that as admin. I mean, this is like obviously an issue which they're aware of, and as far as I'm aware, it's going to be addressed in the next version they're working on. I don't think that this wasn't one of the goals of BitLocker from the outset to provide this level of protection. It's mainly as prevent offline attacks. Yes, I would imagine so, but I mean, it depends on. I mean, the TPM is all well and good having one in your machine, but you need something to use it. And in this case, Vista has BitLocker. I haven't actually looked at any secure bootstrap implementations for Linux. Well, this is interesting. I actually think it's BitLocker implementation that allows it. I mean, the TPM is just a piece of hardware. I'm sure it can be configured so that you cannot reseal it as easily. Like, I think this is a BitLocker implementation issue.
You shouldn't be able to reseal it so easily. There should be some type of hash that you should be able to reverse that way.
Yeah, or some assertion of physical presence maybe, but that's kind of hard to do from when you're as high up as the operating system. Yeah. So how do you? Yeah, I mean, that's pretty much impossible to do. How do you, like, what's the difference between popping up a box and sort of, yeah, and users' code seemingly doing the same thing. So, to summarize, expansion ROMs, all they are is blocks of x86 code on a PCI card that's copied to RAM during boot. Before boot. Essentially, because the OS loader relies on a table of services that reside in the BIOS, we can modify this table, and so that when the OS loader calls one of these services, we get control. And ultimately, we can subvert the entire operating system at this point. I talked about PXE, using it as a means of updating the rootkit pre-boot. Detection of these things focuses really on analysis of the expansion ROMs, and you would need a combination of signature checking and some automated, some heuristics, as well as manual analysis. Pretty much exactly the same as you would do for malware analysis. You would run some signatures over it, you would then run some tools over it that may identify it as some variant of another thing, and depending on how successful the tools were, you may have to get your hands dirty and see what it's actually doing. And BitLocker, as it stands, prevents offline attacks only. So if we compromise your machine while it's running, theoretically we can make everything seem okay. And as I talked about with the IOPL and NT set information process, we don't necessarily need to be in kernel to reflash your card. If we're able to get admin, then essentially we can allow ourselves to do unrestricted I/O, and we can just reflash the card in user mode. So I'm going to leave you with some sort of further discussion points. This is a question which I really have no kind of handle on yet. How long for widespread TPM adoption? Certainly, high-end notebooks these days will almost certainly have a TPM, but a lot of them don't still. It's extra cost. What about a working secure bootstrap implementation for every operating system? I'm sure there are proof-of-concept ones for Linux out there, and Solaris, etc. But Microsoft are the first to market with, here's our actual offering, point and click to install kind of thing. So how long for both of these things? Are we talking 5 years? Are we talking 10 years? Like, will it ever happen?
Right after IPv6 gets adopted.
Yeah, that's an excellent analogy there. We could be looking at 20 years or whatever. Yeah. Whose problem is this? And how do we actually fix it? Is it the vendors? Should they add a jumper to prevent updates? Like, realistically, that's never going to happen. When you think about their market, their users don't want to have to take the machine out to reflash it. They just want to download that tool from ATI, double-click it, and have it do everything for them. Perhaps, yeah. Yeah, of course. Should they have a return to factory default? So should they have kind of the misnomer in terms of calling everything a ROM? It's really, we shouldn't be calling it a ROM. Maybe they should actually have a proper ROM on the card in the true sense of the word that we cannot alter. And maybe they should have some means of allowing us to copy that back across to the one that we can change.
Except for update.
Yeah. So you ship a vulnerable, you ship one that has a major bug in it. Yeah. Should we, like a current problem is, supposing you want to know whether you have an actual a proper vendor's ROM on your card, on your graphics card, for example. So you dump the ROM out of memory and you hash it. Then what do? You could go to the vendor's website and try and download every update they've ever done. You'll be lucky enough to find like the most recent one, let alone all the previous ones, and their versioning issues. Maybe we should have some kind of centralized website where vendors are able to submit ROMs and have them have a hash of them. Then at least your first point of call once you've dumped the ROM is to hash it and go see if it's a known good one. And finally, will we ever see malware target firmware, target these kind of techniques? And well, it's an interesting one. Basically, right now, there's not sufficient return on investment for expending the time and effort to actually build one of these things to work across the major graphics manufacturers. When you have botnets with tens of thousands of machines, essentially, if you lose a machine out of that botnet, you'll just go get another machine. When it gets to the point where losing machines out of your botnet is a concern and you have to keep those machines, then we'll see a transition to more rootkit-like techniques and possibly these kind of techniques. But
Is 1 to 5K actually enough space for them to take advantage of that?
typically, it may not be. You're going to have to do some trickery, either compressing the existing image, and all these kind of all these factors add up to making it harder to build the rootkit that's going to work across everyone's system. So right now, I don't think there's sufficient return on investment to do this, but it's an interesting point, and it's also in terms of denial of service and kind of extortion, that kind of thing. We had the CIH virus years ago that nuked people's BIOSes. Well, PCI cards are still wide open, so you could reflash their cards. And
this is a good example of like something more of a direct attack. Someone has internal access, whether you've got some crazy internal IT guy inside. If he ever gets fired, he's got a way back in or a way to take advantage of.
Yeah, exactly. Yeah.
It's a much better internal direct attack than with some type of botnet.
Yeah, I mean, I agree with that entirely. In fact, the kind of scenario, I give that exact scenario for BIOS rootkits in general. Basically, consider like a large corporation where a disgruntled employee gets fired. Their laptop goes back to the IT guys who reformat it, send it out to the next guy. But if you've got persistence through PCI or the BIOS, then essentially you're back on it straight away. Some references here for anyone that's interested. I've also written a paper which kind of goes into these concepts in more detail, and that's available from www.ngssoftware.com. I'll send this slide deck to LayerOne guys because I've also got some extra points at the end, but just kind of things I pulled out the PXE spec, etc. Yeah.
Aside from, you said that the footprint was, the space available is 1 to 5K, you're sharing space in a VGA card, let's say.
Yeah.
With the original software.
Yeah.
But what if you wiped out the original software? How much more space would you need?
Typically 64K, 128K.
Oh, then you could do a lot more with that.
Yeah.
And in fact, you could probably sell it to the user as a feature of silent boot, right? They don't see that ugly.
Yeah, very true.
You might be able to widely deploy it better that way.
Not that I've done a lot of analysis on this, but there's probably code in there that's very rarely called that you could trim out. So you could probably give them like a much neater image of, they're probably bloatware on the way they've developed the firmware. You could or you could even like optimize their assembler to save a few bytes. Okay.
I really like your PXE update deal there, but how do you realistically maintain a boot server on a network?
True.
Hard code the IP addresses there.
You could do that.
Plus, you'd have to failover in case that box was done.
Yeah, I mean, that's why Etherboot is really nice in that it gives you TCP, so you can potentially do HTTP. Though, then again, it's a question of, what if I need a proxy server to get out your enterprise? Really, it's kind of, again, it's probably not looking at the kind of model of we can create a rootkit we can deploy on every machine that's going to work everywhere. This again is a targeted attack that has hard-coded parameters. So yeah, even if maybe we could get UDP out your organization disguised as a DNS request, but
have you worked with a lot of different cards and system biases? Have you run into things like buggy implementations of the E820 stuff, like the MCFG?
Yeah. Not really in doing, well, certainly not in doing the ACP stuff, because that's kind of high level than that. And the reason I chose the int10 hook for this was because, again, it's I'm hooking something low level, but by the time it actually gets called, we're late into the Windows boot. I know the EI guys ran into some issues with the E820 stuff because they've actually, if you look at EI.com, they've done a second version of bootroot that does some more stuff, and I'd recommend checking that out.
How many cards have you run?
Actually, not too many. I went to the Recycled PC store in Seattle and bought a ton of cheap cards. And a trick I found is that even if you nuke a card, if you can, you basically take it out, stick a PCI, old PCI card in, not an AGP PCI Express, stick a PCI card in, boot off that, tell the operating system, tell the BIOS to always use that card. Then you can typically put the other card back in, and then run the vendor tools on it to try and recover it. So none irreparably yet, but a few of them are pretty messed up right now. But over there first.
Remember the older BIOSes, how they used to have lots and lots of options there to do things like turning off the option room and all that kind of stuff?
Yeah.
Would those have been better? Would those be more secure against something like this? If, let's say, vendors out there trying to sell desktop PCs with full.
I guess so, but at the end of the day, it's all down to it'd be nice for the users that want that to be able to modify that, but most users aren't ever going to delve in those settings and actually change anything. Actually, I've just remembered that one of the slides I wanted to put in, a guy from Microsoft pointed me to a website. There was, I think, some BIOS a few years back where a programmer managed to get a backdoor into it that on his birthday beeped "Happy Birthday," and that's a good example of we've talked about getting physical access to the machine or hacking the machine while it's online. But another kind of interesting point is to what extent do you trust the factory this thing came out of and everyone that's had contact with the card. Using what, sorry? You mean just AGP cards in general? Not that I'm aware of, though. One of my I've tested this on PCI, AGP, and PCIe. In terms of the way expansion ROMs work, they are exactly the same across all of them, regardless of how the actual card may work after that. In terms of expansion ROM, they're all the same. So I tried the crappy PCI cards I got first, but then when I kind of got a bit cocky, I moved on to the PCI Express cards and gave them a shot, and they work just the same. So. Cool, thank you very much.
We're going to go ahead and take a short break real quick.